Yeah, he's already changed it.
All
right.
Like that.
Yeah.
I'll tell you.
So you tell by the way.
Oh, by the way,
By the way.
I am making a minor concession. I will do this. I would prefer to have it Tuesday, but we have to get in the Chapter 4 test before Thanksgiving. I'm going to allow this quiz to be retaken if needed. But there was a stipulation, the max you can get is a 90% on the retake. So if you do need that route or you do choose that route, you don't do really well on it and you want to retake it, maximum you can get is 90%. I think it's 40 points. So that would be a 36 out of 40. So if you're at a 34 or 35, I don't know if it makes sense to do it. But like I said, it's not ideal. I would prefer to maybe push it back a little bit. We'll get through everything fine. There you go. Putting it back on.
Yeah.
You undid the whole thing? You didn't just loosen it up, huh? Nice.
I did.
So I will make that concession. We'll need to finish Chapter 4 next week, and then we will take the test right before Thanksgiving. I don't know if it'll be, and actually right now, it typically is a 2-day test. Okay, I don't know if I can make it a 1-day test. That'll probably have to be that. There is a no calculator portion, and even on Monday, it'll be 2 parts. It'll be a no calculator, which no calculator at all, not even the red ones. And then there will be a graphing calculator part, but one will be like 15 minutes and the other will be 25. So you have plenty. You will have enough time for that. All right, so we graph that. We graph the inverse here. Let me just make sure we list that, because what was the original one for f of x? Our xy table. Oh, this is going to act up all period, I bet. So f of x equals 2 to the x. And we did -2, -1, 0, 1, and 2. And we got 1/4. We got 1/2. We got 1. We got 2. And we got 4. And then we took a look at the inverse. And we flipped everything. And that was 1/4, 2. 1/2, -1. 1, 0. 2, 1, and 4, 2. And so we plotted those.
Should be -2. Why?
-2. Thank you. So that 1/4, -2. And then we plotted those. And we got that graph. And we said find the equation. Did we list what the equation is for that?
Yes.
Yes. What is it?
Y equals log 2x.
Log, I'll say base 2. Base 2. So, and it says find the equation. But when you take this and you flip the x and the y, we get x. X equals 2 to the y, and we're asked to get y by itself. And you're like, we can't. Algebraically, you can't multiply by 1. You're stuck. So we do logs. And we got y equals log base 2 of x. All right, so that is the inverse function. And I believe, hold on. We're going to get to define it, evaluate, derive the basic properties, and we'll probably do the 4th one. We'll get to that one. Actually, we'll probably get to all 5 of them. I don't think we'll get to number 6. We'll save that for tomorrow. But we said the inverse of an exponential function is a log function. Correct? We did that yesterday. All right, so anytime you got an exponential function, the inverse is going to be a log. So setting it up right below there, so just using this little case here, using 2 to the x. 2 to the first equals 2. Okay? When I use the inverse, log base 2 of 2 equals 1. 2 squared equals 4. Log base 2 of 4 equals 2. 2 cubed equals 8. Log base 2 of 8 equals 3. I'm circling your exponents here. That is always your answer for a log. So the answer to a log is always an exponent. So 2 cubed equals 8. So when we rewrite that as log base 2 of 8 is going to equal 3. Okay, so it's always going to be the exponent on the base. 2 cubed is 8, 2 squared is 4, 2 the first is 2. All right, here's our definition. X has to be greater than 0. Can't equal 0. We'll talk about that as well. I got a couple other conditions. A is greater than 0. A cannot equal 1. So y equals log base a of x if and only if x equals a to the y. Now, most of you know John Napier invented logs, right? What year did he invent logs?
95.
Okay, not bad, not bad. Not there yet.
1738.
Before that. Before that. So before 1738.
1684.
Before that.
1625.
Above that.
1650.
Below 1650.
1645.
16.
32.
What'd you say?
1615.
Oh, 1 year off. 1614. So 1614. Look at it. He invented logs in 1614.
Well, we have to know this.
I will neither
Bonus
confirm
question.
nor deny that.
Bonus question?
What are those?
Okay.
All right, John Napier. Like this is big stuff. Without Napier's work on logarithms, it's difficult to imagine how Kepler and Newton could have made their great advances in later times. I think this is Latin, not really up in Latin, and I think it's English here because it does say pupkished. So I do think that should be an L. But it was in 1614. It contained 37 pages of explanatory matter and 90 pages of table. So it furthered the furtherment of astronomy, dynamics, and physics. Okay, so this is 1614. So like he's doing all this. He didn't have his TI-84. He couldn't graph it on there. Okay, so I think that's pretty, it actually is pretty amazing. Yeah, I think he had the TI-88, no, the TI-1. So the first one. All right, first case here. There's a bunch of like little things here. First one here, just rewriting. All right, so take this first one. 4 cubed equals 64. Swoop, swoosh, what do you guys call that? Swoop. All right, how do you do this? So you rewrite it. Log, the answer to a log is always a what? So 3 has to be my answer. 4 is your base. Log base 4 of 64 equals 3. And sometimes you'll do this, so this starts with the 4, 64 ends with the 3, however you do it. So you got to rewrite that. It's log base 64, 3. 3 to the negative second equals 1/9. Okay, that's true. 3 to the negative seconds, 1/9. All we're going to do is rewrite it in log form. Log base 3 of 1/9 equals -2. So kind of you're saying to yourself, 3 to the negative second equals 1/9. And now 5 to the 0 equals 1. First of all, make sure that's a correct fact, which it is. 5 to the 0 equals 1. Log base 5 of 1 equals 0. So that's taking an exponential and converting it to log. Also need to be able to take a log and convert it to an exponential. So the first one here, log base 3 of 9, equals 2. Whatever it equals, that's your exponent. Now, I think this is easier because you're writing this as an exponent, and you know whether it's right or wrong. So you're going to say 3 is my base, 2 is my exponent, it equals 9. And if it doesn't equal 9, you did something wrong. What I mean by that is if somebody says, 3 to the 9th equals 2, that can't be right. So that can't be the exponential form. Log base 10 of 1,000 equals 3. Rewrite that. So that means 10 to the 3rd equals 1,000. And log base 2 of 1/8 equals -3. To the -3rd equals 1/8. All right, so just make sure that makes sense. There at the bottom, logarithms of 0 and negative numbers are not defined. You cannot take the log of 0. You cannot take the log of a negative number. I just want to throw that up there just to, why not? Why not? Okay. Well, if you could, how would you rewrite this in exponential form? So I'd say log base 2 of -4 equals some number x. You would say 2 to the x equals -4. Well, 2 to any power, will it ever equal negative? No. What's 2 squared equal? 4. What's 2 to the -2nd? Because some people might say, hey, it might be -2. Yeah, it's going to be 1/4. So 2 squared is 4. 2 to the -2nd, 1/4. It's never going to happen. So you can't take the log of a negative number. Can't take the log of 0. Log base 2 of 0 equals x. You're going to say 2 to the x equals 0. So you got to come up with an exponent where it's going to equal 0. Can't plug in, well, you can plug in 0 because what's 2 to the 0 equal though? 1. It's never going to equal 0. Okay, so you can only take the log of a positive number. Okay, positive. Your exponent can be negative, or that value there can be negative, but not what you're taking, and your base has to be positive. All right, flip that over. So you got there special logs on the top. On the left, put down common log. On the right, put natural log. Common log, base 10. From here on out, if you do not see a base written, it is understood to be base 10. So when you just see log of x, that means it's base 10 automatically. And now from here on out, you should not write base 10. Like, don't write the 10. I just write it as log of whatever. Base E is natural log, which will now be referred to as ln of x. Okay, that is equivalent to log base E of x. But from here on out, you will just say ln. On your calculator, you have buttons designated for common log, log. That is base 10. So if I take the log of 50, okay, I get an answer. If I take the ln of 50, the natural log, I'm dealing with e to what power equals 50. It's not going to be the same as the common log. I think probably now all of your calculators will do bases, different bases. To do a real quick check, this is always the older one, but if you hit math, go down and see if it says log base. It'll be below your screen. It'll be below number 7 there. Does it say base? Okay. You don't have to type in base 10. You don't have to type in base E. You would use natural log or common log. So if you hit log base, it should pop up where you would enter the base. If you look on mine, there's got to be an update to this thing. I think my last one is 10, which it says solver, and after that it repeats. I don't say log base. Did anybody not say log base? Did not. All right, so you guys you're with me. Okay, we got to do old school, but it's fine. But you do have common log here, and then if you look at above it, it says 10 to the x power, so it kind of indicates what base it is, and ln has e to the x power, so it's going to be base e. Do not write base 10 or base e. All right, I said it. Monday, and also in the chapter test, a portion of it will be no calculator. So you've got to be able to take the log, and this is where you just have to understand what's going on with logs. All right, first thing, when you see that log of 10, you know what the answer is. Or do you even know how to interpret that, I guess? Sometimes it's hard to answer.
The answer's 1.
Answer's 1, because what's it saying? How do you know that?
Well, it's log base, so the base is 10, and then it's 10 to what power equals 10.
Exactly, that's what it's saying. The base is 10, so, and we're saying what power, 10 to what power equals 10 is going to be 1. To help, if you get stuck, I would tell you to do this. So it has to equal something, so make this an x. If I rewrite this as an exponential function, my base is 10. 10 to that power has to equal 10. So hopefully you can figure out that way. Log base 2 of 8. That says 2 to what power equals 8? Well, what's that equal? 3. It's not base 3, it's not anything else. It equals 3, the number 3. Okay, to confirm it, you say 2 cubed equals 8. All right, so you're pretty familiar with that one. Next one, think about it a little bit. Log base 4 of 2 is what? Log base 4 of 2. So it's not probably obvious. It's not like boom right there. So you get stuck. Here's what I tell you to do. Say, all right, put it equal to something. You call it x. How do you rewrite that in exponential form? 4 to the x power equals 2. All right, what is that? Anybody know? Andrew?
1/2.
It is 1/2. 1/2 is the same as taking the what? Square root. 1/2 is a square root. You're gonna have to know that. So x is, your answer is 1/2. 1/2. 4 to the 1/2 power is the same as the square root of 4, and that's going to be 2. If you make it 4 to the first power is 4, 4 squared is 16, it's getting bigger, right? What's 4 to the 0 power? 1. Okay, so it can't be 0, but it has to be less than 1. It has to be in between 0 and 1. Because 4 to the first is 4. So you just kind of watch that a little bit. And all right, log base 9 of 1 over 81. All right, you know that just looking at it. Yep. Okay. What's it going to be? It's going to be, Andrew? What do you say?
1/9.
Ooh, no. No, Justin. -2. All right, so now thinking about it. So we're saying, yeah, because you're saying 9 to the 1/9. Okay. You get what? Yeah, I'm not even sure what that is. 9 to the 1/9 equals -2. Okay, so 9 to the -2nd power equals 1 over 81. Basically say, all right, what equals 81? 9 squared, make it a negative. Okay, so you got that. So when we get into the fractions, we get into something that's less than that. All right, there can be some difficult ones to think about. Okay, you might have to set it up and work through it. Okay, some of the others, you just say, all right, what power? Domain. All right, domain can't take the log of what? We just had it on the front of that last page. Can't take the log of 0 or so that has to be greater than 0. Has to be positive. So 5 minus x has to be greater than 0. So depending on how you solve this, I'm going to subtract 5. You could add x. That's absolutely fine. Negative x is greater than -5, but this is just a little reminder here. What happens when we divide by a negative? Flip the sign. So I got x is less than 5. So my domain, always put this in interval notation, -infinity to 5. Okay, that'll be my domain. All right, copy this down, and I want you to just think about it first before we start. Copy it down, think about it, what we have to do. You got 2 pieces. They both, you're taking the log of both pieces. Both pieces need to be positive, but just deal with one of them at a time. So x, and I don't really need to worry about the radical underneath there. You got to have a positive underneath the radical anyway. So x minus 4 has to be greater than 0. And x plus 1 has to be greater than 0. So whatever number you plug in for or any number you plug in, it has to make both of them positive. Okay, so you got to think about all the numbers that'll make them both positive. Well, just get x by itself for each one. If I add 4, I get x is greater than 4. And subtract 1, I get x is greater than -1. You can't leave that as your final answer. You got to list it in the simplest form. What would be our final domain? It's basically compound inequality. Matthew?
4 to infinity?
Yes. So it would be 4, they overlap. So it would be 4 to infinity. Okay, and that would be it. So if you think about your number line, the compound inequality, x is greater than -1 would be to the right. X is greater than 4 would be to the right. We'd pick where they overlap. They overlap from 4 to infinity. You just got to be careful there. Don't pick just one of them. You got to find out all the values that make both positive. All right, we're skipping C. We're not going to worry about that. I just want to make sure you know that. Okay, can you graph log base 2 of x without turning it over to the front? Good question. So we'll do that for that first one there. Hey, log base 2 of x. You need to be able to graph this without your calculator. All right, you're not comfortable with this at all. Or if you are, that's pretty good. What is its inverse? What is the inverse of that? Let's start with that. Don't graph it though. I'm just going to list it. So y equals 2 to the x. It's a lot easier to do a table for 2 to the x because I can plug in -2, -1, 0, 1, and 2. So first couple times I do this, I'm going to kind of think back to what I already know. I'm going to go back to the exponential function, which is 2 to the x. 2 to the negative second is 1/4. 2 to the negative first is 1/2. 2 to the 0 is 1. 2 to the first is 2, and 2 squared is 4. So now the inverse is log base 2 of x. To me, it's a lot easier just to take these points and flip them. Now, it's got to match up. So basically what you're saying is I'm plugging in 1/4 here. 2 to what power equals 1/4? Negative second. Like 9 times out of 10, you're just going to try to plug in whole numbers in for x. That's kind of how you've been conditioned. In this case, that doesn't necessarily work. So I'm going to take these numbers and flip them. 1/2 gives me -1. Okay. 2, in this case here, 2 to the negative first equals 1/2. 1, 0. 2, 1. 4, 2. All right, once you get that listed, go ahead and plot it, graph it again. It is what we did earlier. I just wanted to go through it again. And let's see here. 1/4 -2. 1/2 -1. 1, 0. 2, 1. 4, 2. So we got that. Vertical asymptote is at that axis, on that axis. So if it moves, we're going to have to move it as well, which we're going to do on this second one. All right, copy that down. Think using that first one. Think how it's been shifted. Okay, think what the transformation is. So you got negative log base 2 of x plus 3. All right, x plus 3. Mackenzie, you know what the plus 3 does?
Does it move it left 3?
Left 3. So we got it going left 3. And Anthony, how about the negative in front? Reflect over the x-axis. We got anything else going on? No, nothing else. All right, where's your vertical asymptote now going to be? It was at x equals 0. Now it's moved over to -3. Draw that in there. I do want you to draw that in there. So draw in that. You will need to be able to graph log base 2 of x. Okay. without your calculator. Okay, so you kind of got to know that. Let's take your points. I'm going to graph the original function and then move it. I know you got it right next to it, which is fine. If you just want to use that, that works. But I'm going to plot these 5 points. And then I'm going to move them left 3 and then reflect over the x-axis. So if I go left 1, 2, 3 over the x-axis, it puts me up at positive 2. Left 1, 2, 3 up to positive 1. Left 3, it keeps me on the axis. Moves that down. And then again, left 3 down here. There we go. There we go. All right, so that looks like should be our final graph. So you got to be able to take log base 2 of x, do all your transformations on that. Left 3, whatever. All right, flip that over when you're done. All right, you see what you come up with for these 4. Take a look at them. What's log base 3 of 3? What's log base 3 of 1? See if you can figure out what they're going to eat. Oh, now the tie's off again. Good deal. Still sore? First 2 tend to be like, okay, got them, and then kind of come to a screeching halt. Third one, not maybe. A lot of people get it. Fourth one, they're like, what the heck?
And then there's another one.
Is it all Asian or answer?
Yeah.
Oh, I'm sorry. Oh, yeah.
I'll put it on those 2, and then we put the pencil.
I don't know, it's kind of weird.
Your dad's military. Yep. Oh, we got the swooping one.
Yeah.
There we go. All right, first one. You're basically saying 3 to what power equals 3? That's going to be 1. 3 to the first power equals 3. 3 to what power equals 1? The only way to take something to a power and get 1, it's got to be what? 0. That's going to be 0. All right, this is a little bit harder. This is saying 3 to what power equals 3 to the 4th power. And now if you write it that way, what's your answer? It's going to be 4. 3 to the 4th power equals 3 to the 4th power. All right, this one throws people off. These were all in log form. Think of this as exponential form. Convert that to exponential form. Okay? Still think of this as an x for right now. So log base 3 of what? Okay, of x equals the exponent, which is, what's the exponent? It's that whole thing. So if I write it like that, what does x have to equal? 4. It's going to be 4. Okay. Now we're getting to the point here where hopefully where you recognize the form, you can just say, oh, it's 4. Okay, this is going to be a property. So you set that. So if you got 3 is your base, and it's log base 3, whatever you have there, that's what it's going to equal. So that leads to these properties here. So these are always going to be true. We just did it for that specific case, but it will also be true. So log base A of A equals 1. I'll just do a quick example beside it. If you need to write it down, fine. If not, fine. But that just means log base 5 of 5 equals 1. Okay, like we just did. Log base A, any base of 1 equals 0. Log base 12 of 1 equals 0. 12 to the 0 equals 1. Okay, if the base matches on the log matches the base in the exponent, you're just going to be left with that x. So log base 7 of 7 to the x will equal x. And then we flip it, kind of flip the order, if this is now my base. So if I have 8, log base 8 of x, that has to equal x. All right. This one's kind of the hardest one to remember. The other ones you can kind of figure out. You can figure out that last one, but it's just not as, I guess, common. All right, all of these work for base 10 and base E, which is what you see on that next little line, or next to. So really, we're not doing anything new. We're just adding the bases. Let me see something here. All right. Oh, no, wait. So log of 10. It's basically saying 10 to what power equals 10? That's 1. Log of 1 is 0. Log of 10 to the x is just x. And then if you do 10 to the log of x, you get back x. ln, automatically what base? E. Automatically base E. So you got to think about that, like ln of e to the x. Throws people off. Natural log of e to the x is just that x. Okay. E to the ln of x is x. Okay, so you got e to the natural log of 2. That is 2. If you got natural log of e to the 4th power, that is 4. Okay, for that case. All right, yeah, let's cover this. Is that on there? Okay, so consider f of x equals a to the x, and f of x equals log base a of x. Okay. Hey, what have we've always taught you? F of f inverse, if you take a function in the inverse of x, what do you always get back? You always get back x. Okay, you always get back x. Okay, now there's going to be something a little bit different here. If you got your calculators, keep those handy. Let's make this base 10. I just want to show something. So if f of x equals 10 to the x, the inverse equals log of x. You agree with that? All right, so what does f of f inverse look like? That is going to look like f of f inverse is going to look like, so you take this, and it's going to be 10 to the log of x. We agree? All right. Graph that. Graph that on your calculator. Okay, 10 to the log of x. Should be able, you should, if I clear that out, 10 to the log of x. Graph. All right, is that what you got? Okay, good. And actually, put an open circle there. Looks like that. Now, f inverse of f of x. F inverse of f of x still equals what? Still equals x. Now, when you rewrite this using those two, what's that going to look like? F inverse of f of x is going to look like you take this, and for that, it's going to look like the log of 10 to the x, right? Matthew, is that right?
Yeah.
Graph that. Graph that. So if I graph, now take your other one out, I'm going to take the other one out, clear it out, and I got log of 10 to the x power. Whoops, that should be a 10. Okay, now let's go up the chain of Bloom's taxonomy here. Why are they not the same? Let's see if we can figure that out. Why are those graphs not the same? Okay, one of them just started at 0, went to the right. The other one went the whole way. Now they're really both the equation. They're both the graphs y equals x. Okay, except one doesn't have the whole domain. Why are they different? Oh, Andrew says I got it.
Because in the first one, you can have a negative number to the log. And the second one, a negative power becomes not a negative number.
All right, no, that's really good. Right here, this is 10 to the log of x. What are you plugging x into? You're plugging it into a log. You cannot take the log of what? 0 or negative numbers. I cannot plug in -1, -2, -3 here. That is why that graph starts at 0 and goes to the right. Christian, how are we doing? Oh, okay. All right, so this one here, you're taking the way we rewrite it, you write it as log of 10 to the x power, which this is an exponent. You can plug in a negative for an exponent because, 10 to the -1, that's 1/10. You still get an answer. So that's a little bit like dealing with the little details there. Cannot take the log of a negative number. That's why when you graph this one, it started at 0 and went to the right. This one contained the domain was all real numbers. All right, let's get through that last one now. All right, I'll let you think about it first. Using our properties, think how we can solve that. I want to solve for x. What does x equal? Okay, what does x equal?
Would it be 3x plus 5 equals 14?
It would be. Okay. Now, here's why you got to be able to apply those properties. On above that, what was the one property wrote down? The natural log of e to the x equals what? Right above there. Equals x, right? So now you got to be able to throw other expressions in there. So whatever this is, whatever this power is, has to equal that answer. So 3x plus 5 has to equal 14. And now we can solve it. I get 3x equals 9 divided by 3. X equals 3 for that one. All right, now let me also talk about that just for one more second. Natural log of e to the 3x plus 5 equals 14. Okay, if you get stuck, brain freeze, like you can't think of it, you forget about it. How do you convert this to exponential form? Now, here's one thing you got to be careful of. That is not your base. That e is not your base. That is what you're taking the natural log of. So how do I convert that to exponential form? Okay, Andrew.
Convert the ln to log of e.
I don't even need to do it. What would be the? It still has a base of what?
So
E.
e to the 14
E to that 14. So yep. So there's that unwritten e.
equals e to 3x plus 5.
So this is another way to go about is getting 14 equals 3x plus 5. This way is easier if you recognize that, but if you don't, you still got an option. All right, whew. Good job. We had to get through all that. I know it was a lot. We'll clean up a few things tomorrow. There's just like one or two little details we need to go over. Well, there might be bigger details. To solve a couple problems. Hey, again, some of these problems are like no calculator problems. Being able to figure that out. Check your answers in the back of the book. See if you're getting enough, so that we can answer any questions you got tomorrow. Go over them. Okay, for that.